afternoon, everyone, and welcome to the final ECE Day Senior Design presentation. We are Team nanoTRACK, and we will be presenting a custom-designed printed circuit board for the Altium Digital Design NanoBoard kit, and we will be demonstrating its functionality using a color threshold to track an object. Allow me now to introduce our team. This is Tunde, Nickvash, Mohammed, Dan, and I'm Schuyler. And today with our talk, we'll be outlining what our customer wanted us to do for him, namely develop a new peripheral board for the Altium NanoBoard FPGA development kit. We will talk about our solution to the board that we developed. We'll go over the hardware, and we'll go over the software that's running on it so that we can actually track an object. So now I'm going to turn it over to Dan, who's going to talk about the customer problem and the board.
So before we can really understand what our project is all about, we need to know a little bit about what the NanoBoard system is all about. So it's very similar in its capabilities to that of the Xilinx development kits that we all know and love from digital design, our digital design courses. Pictured here is the NanoBoard 3000. At its center, there's an FPGA as well as a number of peripheral devices that you can play around with. The unique thing about these NanoBoard systems is that you can continually augment and enhance the functionality of the NanoBoard system through the addition of custom-designed peripheral boards. You plug these peripheral boards into your NanoBoard system, and you have access to a whole new set of peripherals. This allows Altium to constantly update the peripheral devices that they offer for their boards. Pictured here is a Ethernet networking board as well as an external memory board developed by Altium. So when our customer approached us in September, he wanted us to develop a new peripheral board specifically for imaging and video applications. And our solution to this problem was this. This is a custom-designed Team nanoTRACK peripheral board. As you can see, this is the layout of the board taken from the Altium Designer CAD software. And there's a lot on here, so please allow me to just go through some of the main components. The centerpiece of our board is an analog BF561 digital signal processor. This is one of the top-of-the-line digital signal processors offered by Analog Devices, and it's specifically designed for imaging and video applications. It has a dual-core architecture, and it runs on 600 megahertz, so it's a pretty fast processor. The processor also has the benefit of 32 megabytes of external SD RAM. This provides a place for the incoming video frames to be stored, as well as 64 megabits of external flash. This provides a non-volatile source from which the DSP can boot startup code, and we're using that in our demonstration. In addition to these devices for the DSP, we have a number of video input and outputs. And the real theme I want to drive home here with this board is that the driving force behind our design is versatility. We want this board to be suitable for a whole variety of different applications. And with that in mind, we support a whole different set of video inputs and outputs. For example, we have an S-video input, a composite input, an S-video output, composite output, and a VGA output. Now we go to the back layer of the board. This is a 4-layer board. The top layer has a 3.3 volt ground port, and on this bottom layer we have a digital ground port. Some of the additional features we have are an RS-232 connection, again, which we'll be using in our demonstration. This provides a serial interface to the digital signal processor. We have a JTAG programming interface, which provides for a debugging source as well as a place to program our digital signal processor. And we also have this peripheral board connected. This is a key component because it's the main interface between our board and the NanoBoard system. It plugs directly in and allows us to access all the functionality on this board. Again, with this idea of versatility in mind, we have a variety of encoders and decoders on this board, and they're all highly configurable. We can control the incoming video brightness, color saturation, hue, and a whole variety of different video parameters. And we can configure these through I2C. The I2C configuration is a multi-master configuration, which allows developers to program the decoders with either the DSP or the FPGA. Finally, just some words about how I designed the board. As I mentioned before, this bottom layer is a digital ground port, and I have a separate analog ground port on one of the inner layers. This helps separate some of the sensitive analog circuitry from the fast digital switching of the DSP. And finally, the board is 4.5 inches by 4.7 inches in size. Again, conformed to fit into the standard NanoBoard condition. Now, Tony is going to talk about the specific application that we developed for this board.
As Dan mentioned, the purpose of the nanoTRACK, the custom nanoTRACK peripheral board, is for video processing applications. So what Team nanoTRACK will actually be doing is we'll be tracking an object. Specifically, we'll be tracking a brightly colored orange output. And to track this, we'll be using the DSP. And the DSP will input the incoming video image and apply a color threshold on it, specifically looking for the color we're looking for, which is right now. Then it'll perform a PID control algorithm on the data, send it out to the FPGA, which will then drive the servo mechanisms. And specifically, we'll be testing it with a printed. So here's a high-level system block diagram. And basically, the nanoTRACK peripheral, we have three components. We have the FPGA, which is located on the nanoboard. We have the camera with the pin tilt servos. We also have the nanoTRACK peripheral board. And basically, all the heavy lifting, all the image processing will be done on our custom-built nanoTRACK peripheral board. Here's Nick. We'll talk about the process a little more in depth.
All right, so now that you have a general idea of the basic system, let's go through it once in a bit more detail. The first thing to mention is that this board, this is a picture of our peripheral board, and surrounding it you'll notice the FPGA, so this is as it is plugged in. The video comes in through the composite video port and it enters a video decoder chip, which is then connected to the PPI port of the DSP, and the video data is promptly transferred to the SDRAM. After it's transferred to the SDRAM, the DSP again reads the video data and performs a color thresholding algorithm to isolate the correct object. After it has the correct object, it performs a center of mass calculation, which calculates the coordinates of the object with respect to the current frame, and passes that data along through a control algorithm, which will determine how the servo should move to keep the camera within the correct view. After it has that data, it passes the control data packets through a UART board and back to the FPGA. Once it passes it to the FPGA reads it and then performs a PWM calculation, which is sent to the servos to perform pan and tilt. And let me pass it back to Tunde to go into the DSP software.
So this is the DSP software flowchart. And at the beginning of the program, all the necessary variables, the system services, and the device drivers are initialized. Specifically, we'll be using 2 video frames, which will be declared in SDRAM. And we'll be using 2 video frames. So while the motion tracking algorithms are performed on 1 video frame, the PPI, which is a controller on the DSP, which processes, which means it processes the data, which means it gets the frame from the decoder and places it in SDRAM, will be processing the frames. So first thing it checks to see the frames processed, and what happens is when the PPI successfully processed the frame, which means it was placed in SDRAM, it calls a callback function, which is basically the same thing as it's just a software name for it. It sets the next frame, the process flag, and then it signals the DSP to start the motion tracking algorithms. It performs center of mass and control algorithm, then sends the data out through UART, and then checks to make sure the next frame is processed. So as it performs the motion tracking algorithm, the PPI will be processing the next video, placing in SDRAM. And once that the next frame was successfully processed, it sets the current frame to the next frame, and then sits in a while loop. So here's a example image of what the camera inputs onto the DSP. This is taken directly from the SDRAM. And as you can see, we'll be tracking the bright orange block. And what happens is the DSP looks for, it compares every other pixel, the CV and the CR values for a specific color. And it sets we set a binary image, which is black if it's orange, or white if it's not. And as you can see, this is the outcome. And the line going down are the center of mass. And what we do is take the center of the image, and we calculate the pan and the tilt error. And then after we get the pan and tilt error, we can then pass it on to the control algorithm. And Schuyler will talk a little bit about that.